This is lecture 15 part 2. So in last part we have started time domain analysis. Today we'll be discussing the time response of second order system. So this is second order system. Let us first draw the block diagram. So suppose we have that forward path transfer function, that is omega n square divided by this s into s plus twice zeta omega n, and if we close this loop, this is that comparator and we have that reference command. Whenever we take that negative feedback, we have this output. Then if we find transfer function from reference command rs to ys, we will get a transfer function which is omega n square divided by 2s square plus twice zeta omega n s plus omega n square. So this is a standard transfer function model of second order system, and here we have introduced two parameters. One is that zeta, another one is omega n. So in second order system transfer function model, this omega n is known as that natural frequency, unit is radian per second, and this zeta, it is called that damping ratio. Why it is called ratio, I will be discussing just now. That is, it is that ratio of two damping factors. One is that actual damping factor divided by that critical damping factor. So now the question is, what is critical damping factor? So that thing we will discuss later. Interestingly, we have seen that in case of first order system, the time response is characterized by its time constant. But in case of second order system, the time response is characterized by these two parameters, that is zeta and omega n. So that is the dynamic behavior of second order system is characterized by two parameters, those are zeta and omega n, and this zeta is that damping ratio and omega n in natural frequency. So now if we find the characteristic equation of this particular closed loop system, so then we have already learned that if we write the denominator polynomial is equal to 0, it gives that characteristic equation. So this one, So that is the characteristic equation. If we write characteristic equation, so that is a square plus twice zeta omega n s plus omega n square equal to 0. So what are the poles of that system? So the poles are, that is minus b plus minus root over 4 zeta square omega n square minus 4 omega n square by 2. So this one equal to minus zeta omega n plus minus, if we take omega n, 4 omega n square common, so that one would be omega n root over zeta square minus 1. We can also represent it as minus zeta omega n plus minus j omega n square root 1 minus zeta square. So these are the two poles of this second order transfer function. And here you can notice, that means if we apply a step input to this system, that means if this rs is a unit step command, then if we apply final value theorem here, then we will see that s equal to 0 and s equal to 0, because final value theorem, it is limit s tends to 0 sys, as rs equal to 1 by s. So then basically the steady state value would be equal to 1. So that's why this particular form is called that normalized second order transfer function. So I hope you understand why it is called normalized, because if we write that 1 by, if I write that 1 by omega n this term, then steady state value would be 1 by omega n square. But as we have represented the transfer function in normalized form, that means omega n square by this term, so omega n square by omega n square will be cancelled out and it would be 1. So that's why this particular transfer function model is called that normalized one. And now we'll see that in this, for this particular normalized transfer function, second order transfer function model, we have two poles, and this particular term, this zeta omega n, is defined as sigma. So this is called that damping factor. So this is defined as damping factor. So then the two poles becomes that S12, that is equal to minus sigma plus minus j omega d. So now you can see that there is another term defined as omega d. So this omega d is omega n into under root 1 minus zeta square. So then this is omega n into 1 minus zeta square. So this particular term is called that damping frequency. So it has that physical meaning. Whenever that system is operated under damped condition, then there would be an oscillation, and the frequency of that oscillation, that means in under damped condition, the oscillation of that system, if we consider that oscillation, then that frequency of that oscillation is omega d. So that's why it is called that damping frequency, and its value can be calculated as that natural frequency, that is omega n into square root 1 minus zeta square, and we have seen this zeta is damping ratio. So the damping frequency is that rad per second, its unit. So now let us see that if sigma is that damping factor, then if we go back to that definition of damping ratio, what we can see, that is that actual damping factor. So actual damping factor is that sigma, that is zeta omega n, and the critical damping factor. So critical damping factor means this is the damping factor when the system is critically damped, and when zeta equal to 1, when zeta equal to 1, it is called that critically damped. So critical damping factor in this case would be omega n only, because sigma equal to zeta omega n, and whenever zeta equal to 1, so then that is that critically damping factor is only omega n. So we can see that actual damping, that is zeta omega n divided by omega n, that is equal to zeta. So that's why this is actually the ratio of two damping factors. That's why this name is called that ratio, and it is unitless quantity. So now let us see what happens if we apply that step input to the second order system. And here we have considered the transfer function of the second order systems in normalized form. So before going into that, so let us see the location of these two roots. So two roots are minus sigma plus minus j omega d. So now if we plot these two poles in that imaginary, in the complex plane, then what we would see, that is that real part of that complex plane, and this is that imaginary part. So now that is minus sigma. So minus sigma, that means in the left hand side, the negative side, that is that sigma, of course that is minus sigma, and plus minus j. So here you have one pole and here you have another pole, they are complex conjugate, and here we can see that this is actually omega d, and positive side plus j omega d, negative side minus j omega d. So that means this particular length, that is omega d. So omega d equal to omega n 1 minus zeta square. So now if we just connect that point, this pole location, with that origin, so we'll be having one angle, that is theta. And let us see what is that hypotenuse. So that is under root, that is sigma square plus omega d square. So that sigma is zeta square omega n square, and omega d, here you can see that omega d is this one, so that is plus omega n square 1 minus zeta square. So omega square minus zeta square will be cancelled out, so that is equal to omega n. So this hypotenuse, this length is omega n. So now if you take cos theta, if we take cos theta, so that is that base by omega n. So base by omega n, sigma equal to zeta omega n divided by omega n, that is equal to zeta. So that means if you have a pole here and if you connect this origin, so this is that origin with that pole, then it gives you some angle, this is that angle theta, and if you take cos of that theta, it gives you that damping ratio. So in case of a second order system, whenever you have two poles, and just by plotting those two poles in complex plane, directly you can find what would be the damping ratio. So after getting this theta, you take cos of that theta, it gives you the damping ratio. So let us now see what happens if we apply a step input to the second order systems. Whenever you apply a step input here, unit step command, then what would be the response? So that is actually our objective. As we have pointed out, the dynamic behavior of the second order systems depends on that zeta and omega n. So now we will be just concentrating on that zeta, that is the damping ratio, and we will see the different behaviors of the second order system. So the first case is, so this is actually that unit step response. Unit step response of second order system. So the first case is that underdamped case. So underdamped case is that zeta value varies from 0 to 1. So let us first derive the time domain expression, that is that yt. We have already done those things in Laplace transformation, and I would suggest all of you to do it again. That means this ys by rs, the normalized transfer function is omega n square by s square plus twice zeta omega n plus omega n square. So I'll be writing the denominator part in factor form, and we have seen that it has two poles, that is zeta omega n plus j omega d. So it has one pole, and another pole is s plus zeta omega n minus j omega d. That thing we can see from here. It has two poles, s minus of that, minus and minus, it would be plus, and then one is plus, one is minus. So then we have applied that rs unit step, that means rs equal to 1 by s. So then ys would be equal to ys, that one equal to omega n square, and in place of rs if we write that 1 by s, so then it would be s, and we have that two factors. So s plus sigma zeta omega n plus j omega d plus s plus zeta omega n minus j omega d. So now if you take inverse Laplace transform, so first we need to factorize it. So if you factorize that one, we have already derived those things, s plus zeta omega n by s plus zeta omega n square plus omega d square zeta omega n s plus zeta omega n square plus omega d square. So now if you take inverse Laplace transform, so you will get that expression of that yt. So that thing would be 1 minus e to the power minus zeta omega nt omega dt plus zeta. So I would suggest you to remember this particular expression, otherwise you need to derive all the time. And if you just simplify this one, you would have zeta omega n t divided by square root 1 minus zeta square and sine of omega dt plus tan inverse 1 minus zeta square by zeta, and this is for t greater or equal to 0. So we have derived that particular expression in Laplace transformation, and here we can see that whenever zeta in between 0 to 1, so then the response is called that underdamped response, and we have that yt. So this is that expression. So later on we will see what would be the time response. We'll be plotting the response later. So now let us see the second case. So the second case is undamped case. So undamped case means, you know, there is no damping. So undamped case, that means the damping ratio would be equal to 0. So the damping factor equal to 0. So in this undamped case, so if you just put that zeta equal to 0 here, zeta equal to 0, zeta equal to 0, and if you just put all the things and if you simplify that one, then you will get that yt equal to 1 minus cos of omega n t. So the important thing is, this is that undamped case when zeta equal to 0, and this is that underdamped case whenever zeta varies from 0 to 1, and this is the third case whenever that zeta equal to 1. That means this is called the critically damped case. That means whenever zeta equal to 1, so then the system is critically damped. Then what happens? So here if you just apply, so in this particular expression if you just apply that limit, then what will you get? So I am just writing it here. I would suggest all of you to derive it on your own. So that zeta tends to 1, then here you can see this is that sine term. So here you have that term sine omega t, omega dt divided by 1 minus zeta square, and here you have that sine omega d means omega n 1 minus zeta square into t divided by 1 minus zeta square. So if you take the limit of that, it gives you the value omega nt. And then if you simplify it, if you simplify this particular expression, taking this particular result, you will get that yt equal to 1 minus e to the power minus omega nt into 1 plus omega nt. So I suggest you to derive these expressions on your own. So here we have seen this is the third case whenever that zeta equal to 1, and this is that critically damped case. Then the fourth one is that overdamped case. That means whenever zeta is greater than 1, that is that overdamped case. So overdamped case is zeta greater than 1. So if you just apply that Laplace transform and inverse Laplace transform, so you will get this expression. I am just writing that expression, this yt equal to 1 plus omega n by 2. Here I am writing zeta square minus 1, zeta is greater than 1, and you have two poles. One is that s1t divided by that s1 minus e to the power minus s2t divided by s2, and of course this time expression valid when t greater equal to 0, and here you have that two poles already you have seen, that is that zeta plus zeta square minus 1 into omega n, and s2 that is zeta minus zeta square minus 1 omega n. Mind that this zeta is greater than 1. So this is that expression. So what we have seen now, so that means whenever we have a second order transfer function in normalized form, so we can realize that this particular transfer function as a closed loop feedback system, and here you have that input and you have applied that unit step function here. Then we are interested to see what would be the output, and here we have considered 4 different cases depending on the values of zeta. The first case is that underdamped case, the second case is that undamped case, third one is that critically damped case, and this is that overdamped case. So among those 4 cases we will be considering that underdamped case in detail. So let us see what would be the response in case of underdamped situation. So now we are going to plot the response, step response of a second order system. Transfer function is given in normalized form in underdamped situation. That means the second order underdamped response. So here first we draw the time axis. So this is the time axis, and here you have that output yt, and we have applied here that unit step command. So this is 1, this is 1, and we'll see that the response is like this. The response is like that, and this is actually that zeta is less than 1 greater than 0. That means this is that underdamped situation. And here I'll be pointing out some values in the time response. So one value is that 50%, that means 0.5 of 1, and suppose this time is TD, and then if we take that 10% here, so this is 10% of that final value is 1, so the 10% of that is 0.1, and here suppose this is 90% of the final value, that is 0.9. So here this is the time, and this time I am just labeling as, denoting as TR. Now the another one is, suppose this is the time where the first peak appears, so suppose this time is TP, and now if we take say 2%, plus minus 2% band with respect to the final value. So final value is 1, so plus minus 2% band means here we have that 0.98, and on above it has 1.02. So this value is 1.02 and this value is 0.98. That means we consider plus minus 2% band with respect to the final value, steady state value. So I am labeling those values on the time response of a second order systems, and here suppose this is the time, whenever that system response enters and stays inside that plus minus 2% band. So this time I would say this is TS. So in case of this second order system time response, we define some terms, and those are delay time, rise time, peak time, settling time. So these are the 4 terms are used to characterize the time response of a normalized second order system. So let us see what is called delay time. What is delay time? So delay time is denoted as TD. So here you can see this time is TD. So that means this is the time required to reach 50% of the final value. So this is defined as the time required for the step response. That means the input should be that unit step to reach 50% of its final value. So that means the delay time is TD, and from this figure it is clear that this is the time you need to reach 50% of the final value. Then what is rise time? So rise time is denoted as TR. So let us see what is that. Here we have seen that TR is the rise time. That means this is the time required to go from 10% to 90% of the final value. That is called that rise time. So this is defined as the time required to go from 10% of the final value, 10% of the final value. So here final value is 1. So 10% of final value means that is 0.1 to 90% of the final value. So this is called that rise time. So from this figure it is clear that this TR, that is that rise time, that means the time required to go from 10% to 90% of the final value. And then what is peak time? So peak time, you can see whenever you apply step input, then you have first peak, second peak, third peak, fourth peak, like that. So basically the time required to reach the first peak, so this is that first peak, that means the peak time is defined associated with the first peak. That means the time required to reach the first peak of the time response is called that peak time. So that is the time required to reach the first peak. So mind that that is that first peak. So it is clear from that particular plot. We have another definition that is called that settling time. Settling time, it is denoted as TS, and we can see here that means we have taken a band that is plus minus 2% with respect to the final value. So here the final value is 1, and if we take plus minus 2%, then we can see that this is the time required to enter and stay inside this plus minus 2% band. That means this oscillated response enters and stays inside this plus minus 2% band. So after the time Ts, so this Ts is called the settling time. So settling time is defined as the time required for the transients damped oscillation to reach and stay That is important. The reason is you can see that this response actually here also it reaches but does not stay inside that plus minus 2% band, because after some time it goes out again it here. But you see, this is the point where it first reaches and stays inside that plus minus 2% band. So that's why by definition that damped oscillation to reach and stay within plus minus 2% of the steady state value. So that is called the settling time. So now the question is why the 4 definitions are required, or what are the importance of those 4 definitions. This is very simple. So if you know the delay time, rise time, peak time, settling time, or at least 2 or 3 among them, then it is easy to characterize the time response of a second order system. That means you know when the first peak would come, when the second peak would come, so like that. But from those 4 definitions you won't be able to say, that means how much peak would be there, how much peak. So to quantify that one, we will be introducing another definition which is called that percentage of overshoot. We will be discussing later. So now the point is how to calculate those values, how to evaluate those values. So first we will be considering the peak time. So now if you just see the time response, you can see that at the first peak, if you get the slope would be equal to 0. So let us take the derivative of this particular expression, because this is that yt equal to this one, and this is the case what occurs in underdamped situation. And if we take the derivative of that yt and if we just equate it to 0, then it gives you the time when the first peak occurs. So yt, we have 1 minus e to the power minus zeta omega n t. I am just copying it from there, copying that same expression, this expression, sine omega dt plus tan inverse 1 minus zeta square by zeta. So then if you take derivative of that dyt by dt, what we get, that is omega n minus 1 by under square root that 1 minus zeta square e to the power minus zeta omega n t sine omega n 1 minus zeta square t. So at the first peak it should be equal to 0. So then if you just solve this one, you will get that omega n. So this implies that omega n 1 minus zeta square t equal to n pi, where n equal to 0, 1, 2, 3, so on. So here we can have that t equal to n pi divided by omega n 1 minus zeta square. And one interesting thing you can see here, when n equal to 0, then t equal to 0. So that means at t equal to 0, the slope is 0. And this is very interesting. That means if you look at the time response here, you can see that the response is starting like this. It is starting like that, like this. But if you see the first order response, you can see that it is starting like that. The reason is, in case of second order system, so this is actually the second order system, and this is that first order system. This is that first order system. So in case of second order system, at t equal to 0, the slope is 0. But in case of first order system, here the slope is the inverse of the time constant. That thing we have seen. In case of first order system, the slope is a, or 1 by t. That means this is the time constant. And in case of second order system, the slope is 0. So this is very important. Later on we will again discuss why it is so important. So in case of second order system, the slope is 0 when t tends to 0, and in first order system that slope is the inverse of the time constant. So this is the difference. This is the difference with first order step response. You should remember this thing. And at t equal to Tp, that means n equal to 1, here you can see. So t equal to Tp means, you can see here, this is the Tp, and the first peak occurs at Tp. So at t equal to Tp, what you get here? So Tp equal to n equal to 1, so that is pi by omega n 1 minus zeta square. So this is that expression for the peak time. So you can see here, that means whenever zeta varies from 0 to 1, then you have this response, this is that underdamped response, and that peak time Tp is equal to pi by omega n into square root 1 minus zeta square. That means whenever a transfer function, normalized transfer function is given to you, and once you know the value of zeta and omega n, so directly you can find at what value that maximum the first peak occurs. So now we can see, that means at t equal to Tp, suppose you have the maximum peak, that is y max, and if you just subtract this y max, subtract this final value, that means here this is 1, so I max minus 1, then you will get this particular peak. So now we are just trying to quantify, that means how much peak we will get. So this is quantified in terms of percentage of overshoot. So it is also represented as percentage of overshoot. So what is that? It is defined like that. That means y max minus 1, that is final value, divided by 1 into 100. So this is called that percentage of overshoot. So let us see what is y max, because we get when that y max occurs, that is that yTp. So at t equal to Tp we get that one. So now if we just replace that Tp here, Tp here, Tp here, then we can get that simplified value, that is yTp equal to 1 plus e to the power minus zeta pi divided by 1 minus zeta square. And now you can see the definition of that percentage of overshoot. So now if you bring that one to left and divide by 1, so we have only this term, that is the percentage of overshoot equal to e to the power minus zeta pi divided by 1 minus zeta square into 100. And one interesting thing you can notice here, that means that peak value, that is that percentage of overshoot, does not depend on omega n. It does not depend on natural frequency. It only depends on the zeta, that means that damping ratio. So let us now calculate. So here actually we have defined that peak time, rise time, delay time, settling time. So we have done that peak time. So now what would be the settling time? I am not going to derive that one. I would suggest you all to derive it. So I am just going to give you the relationship, that is that TS, settling time, TS, this is nearly equal to 4 by zeta omega n, and here I am showing you how to calculate it. That means if you look at that time response, you can see that those peaks, this is the first peak, second peak, third peak, like that, and they actually follow one exponential decay curve. And now you need to find at what value it first reaches and enters and stays inside plus minus 2% band. Then you can take some simplification, some approximation, and finally you will get that settling time. It is nearly equal to 4 by zeta omega n, and mind that here we have taken plus minus 2% band. In some cases also 5% band is considered. That means in place of plus minus 2%, if you take plus minus 5%, so in that case though that value would be different. So basically whenever you are asked to find what would be the settling time, so that considered band is important, whether you have considered plus minus 2% or plus minus 5%. So here I have given you the settling time TS, that is 4 by zeta omega n, that is for plus minus 2% band. Then the other two terms, that is the delay time TD, and rise time TR. So for this delay time and rise time, there is no such explicit relationship. So we can take one second order system, and just by varying that zeta, as there is no explicit relationship with zeta, that means the damping ratio and TD and TR, what we can do, we can vary that zeta and we can plot what would be the delay time and rise time from the response, and from there just by fitting a curve we can get a relationship. So one relationship is as follow, that is the delay time is nearly equal to 1 plus 0.7 zeta divided by that omega n, and of course it is clear that this particular relationship holds whenever zeta is varied in some particular range. So whenever zeta varies from 0 to 0.9 like that, you know this particular relationship holds. And in case of rise time, we follow the same technique, that is 0.8 that zeta divided by omega n. So let me repeat, that is in case of second order system we have just considered that underdamped case, and here we have defined the delay time, rise time, peak time and settling time. So from this particular definition and time response, it is clear, that means what are those delay time, rise time and peak time and settling time, and what are the utilities of those definitions, because if you know those values easily you can characterize. But from those four definitions it is not possible to know how much peak will be obtained from that particular response. So for that one we need to quantify, and it is quantified in terms of percentage of overshoot, and then we can find the peak time percentage of overshoot directly from that expression of that second order system YT. But for settling time we need to do some approximation, but for delay time and rise time we do not have any explicit relationship with the zeta value. So how can we get those relationships? First, if we have a second order transfer function and if we vary that zeta, then we will be getting different TD, delay time and rise time, and then just fitting a curve we can get that relationship, and here this is that relationship, that is delay time and rise time. So next we'll be discussing, that means what are the qualitative responses whenever we consider the different values of zeta. So here we have seen the four different cases, that means whenever zeta varies from 0 to 1, that is underdamped case, and when zeta equal to 1, that is critically damped case, when zeta equal to 0, that is undamped case, and when zeta greater than 1, that is overdamped case. So now we'll be looking at the location of the poles, that means in those four cases what happens. So let us see, that is that step response. Corresponding to various pole locations. So here we are analyzing the same thing in terms of the pole locations. As we have seen, the location of that poles of a second order system, that is S1 and 2, we can see here. So the location of that poles here you can see, that is minus sigma plus minus j omega d. So we can see here minus sigma plus minus j omega d, that is zeta omega n plus minus j omega n 1 minus zeta square. So now whenever it is overdamped case, so if it is overdamped case, that means zeta is greater than 1, so that means overdamped case, so this is that complex plane, that is that real axis, and this is imaginary axis. And we can see here that if we take j inside, that means zeta square minus 1 and zeta equal to zeta greater than 1. So when zeta greater than 1, you can see here this is negative and plus minus some negative value, that is square root zeta square minus 1. So that means here this is the case S12, that is zeta omega n plus minus omega n square root zeta square minus 1, because here zeta greater than 1. So this is that overdamped case. So in case of overdamped, what happens? The time response is like this. This is that overdamped case, and here you can see this is that time and this is that output yt. And what are the pole locations? So both of them are actually the real poles, and here you can see that zeta greater than 1. So that means both of them are the real poles and they are lying in the left half of that S plane. So this case is actually that overdamped case. So now I think you can understand, that means in case of overdamped situation when zeta greater than 1, you have this yt, and if you plot that yt, you will get this type of response. So that means there is no peak, no oscillation, and the location of the poles are on the left half of that complex plane. That thing you can understand from here. Now the second case is that critically damped. So critically damped means that zeta equal to 1, and whenever that zeta equal to 1, you can see here, if you put zeta equal to 1, so this term would be equal to 0. So you have two poles are on the same location and they are real and negative. So you have two poles on the same location, they are real and negative, and if you just look at that response, the response is like this. So response is like that. So critically damped, that means a little bit faster than that overdamped case, but there is no peak. So these all are the 0. So this is actually the case of critically damped case. So the interesting point is, in case of critically damped situation, we have derived that expression of yt. So now we are showing that qualitative response and the pole location. So both the poles are on the same location on the real axis and they are negative. Now let us see what happens in case of underdamped situation. So underdamped situation means that zeta is varying from 0 to 1, and you can see here whenever you are varying zeta 0 to 1, that means it is positive, So you have that complex conjugate pole. So you have that complex conjugate pole means, so one pole is here, another pole is here, and as we have discussed, that means whenever you have that pole location, if you just connect it, if you just find that theta, that cos theta would give you that zeta value, and once you vary the location of that poles, you can see that theta would be also varying and the zeta value also will be varying. So now we are interested to see what is that underdamped response. Already we have discussed in detail that underdamped response, that means there would be some oscillations, that just now we have discussed, there will be some oscillation. So this is that case of underdamped response. And you look at the pole location, so both of them are actually complex conjugate poles. So now let us see what happens in case of undamped situation. So undamped situation means, so here you have that real axis, imaginary axis. So this is that case whenever that zeta equal to 0. So whenever zeta equal to 0, you can see here, if you just put zeta equal to 0, so then you have this one equal to 0, and only you have plus minus j omega n. This is equal to 0, this one, so this one equal to 0 and this one equal to 0. You have only two complex conjugate poles, but real part is 0. That means both of them, both the poles are on the imaginary axis. So then what would be that response? It keeps on oscillating. So that means here the two responses, so here you can see that S1, 2, you have two poles which are actually complex conjugate poles, and they are on the imaginary axis. So then if you apply that step input, so it keeps on oscillating, and that oscillation is that natural oscillation, you know, that omega n. So this is actually undamped case. And next what happens? So we can see that two poles on the real axis, but they are different. So that is that overdamped case. They are on the real axis, but they are at the same location, that is critically damped case, that corresponds to zeta equal to 1. Zeta equal to 1, and whenever they are complex conjugate poles, the zeta varies from 0 to 1, that is that underdamped case, and whenever zeta equal to 0, that is that undamped case. So next, if the poles, two poles, moves to the right half of that complex plane, so obviously that would be unstable, as we have discussed. So if two poles are complex conjugate poles but unstable poles, then what would be that response? So this is T, this is that YT. So here you have that YT. So then the response, it starts oscillating, and then you know that it is gradually increasing, and finally it would be unstable. So these all are the pure sinusoid type oscillation. And then what happens if it has two unstable poles but they are on the real axis? So this is that real and this is imaginary. This is that complex plane, and you have two unstable poles, but they are on the imaginary axis. Then you can see the system's response would be the unstable one, as the two poles on the right half of that S-plane, complex plane, and the response would be like this. So that is also unstable. So you would say that this is unstable case, this is also unstable case. But here in this case the system goes to infinity through this oscillation, and in this case there is no oscillation, it just goes to infinity when t tends to infinity. So let us see what we have discussed today in this particular part. So in first part we have discussed time domain analysis of first order system, and here this is the time domain analysis of second order system. And there are two parameters, that is that zeta and omega n, natural frequency and the damping ratio. They characterize the response of a second order system, and here we have defined what is natural frequency, what is damping ratio, what is damping factor, what is damping frequency, and we have shown how to find the damping ratio from the poles location. Then we have derived that expression in 4 different cases: under damped case, over damped case, critically damped case, and undamped cases. And then we have concentrated on that second order underdamped response, and we have defined 4 different terms, that is the delay times, rise time, peak time, and settling time, and we have shown how to calculate those values. And also we have pointed out that delay time and rise time, there is no explicit relationship with zeta, so we got those relationships just by getting some data points and fitting some curve to those data points. And then we have seen those 4 different cases along with the unstable cases corresponding to the location of the poles of a second order system. So in next lecture we will be discussing that whenever we add a pole and add a 0 to a normalized second order transfer function, then how the response is changed. Thank you.